Hi, welcome to video 9.10d, Introduction to the Lagrange Form of the Remainder. Okay, so this is probably one of the trickier things that we're going to study in this chapter. So you have a Taylor series near A for f of x. The book calls it C instead of A. We know that Taylor series, okay? That's nothing new. Now what happens though is this is the first, well, n plus 1 terms because you're starting at 0. But then there's the rest of them because it is an infinite series. So if we approximate f of x with the Taylor polynomial of degree n, then f of x is approximately equal to, and you'll stop at n, okay? The error is going to be, now this is the maximum error, is going to be the maximum value of the next term, which will be the n plus first derivative, n plus 1 factorial, x minus a to the n plus 1. And here's the tricky part. It's the n plus first derivative at z, where z is a number between a and x. Okay, so a is the number that it's close to, the one, your Taylor series at a, and x is the next number close to it. So let's say you're trying to approximate ln of 1.2, then 1.2 is your ugly number, and 1 is the pretty number that's close to it. If you were approximating ln of 0.9, then 0.9 is the ugly number, and 1 is the pretty number. And that's why they have to say between, because z could be bigger than a, less than x. It depends on whether your ugly number x is less than or equal to the pretty number it's close to. This thing here is called the Lagrange form of the remainder, okay? So if it's a Maclaurin series, of course, it's the same old thing, but of course it's at 0. So instead of x minus a, it's just x. Instead of f prime of a, it's f prime of 0, f double prime of 0. That remainder is Rn. That's, you're using the first n terms, and the same idea. N plus first derivative of f at z, where z is between a and x, times x to the n plus 1 over n plus 1 factorial. So the way we write it is that the maximum error is going to be a positive error. So absolute value is the following. Now, and this is the key thing that they kind of don't point out in the book. The max, it is a fraction. So remember, a fraction is going to be a maximum. It's going to be the largest it can be when the numerator is as large as it can be and the denominator is as small as it can be. Okay, so here's an example. Find the maximum possible error if you use a Maclaurin's polynomial of degree 4 to approximate the sign of 0.001. Sorry, 0.01. So obviously the number it's close to is 0, right? So our x is 0.01, our a is 0. So here's our formula, although you already know that formula, okay? But since we're using the first 4 terms, the error, maximum error, will be less than the 5th derivative because we went to the 4th derivative. Now the reason you're going to need the table is you're going to need to know what the 5th derivative is, okay? So it's the 5th derivative at z, where z is between a and x, which in our case, z is between 0 and 0.01. 5th derivative at z over 5 factorial, remember n is 4, so n plus 1 is 5, times x to the 5th. Now, the 5th derivative at z we figured out is cosine z because the 5th derivative at x is cosine x. And in our case, where z is between 0 and 0.01. Now, here's the way this works. This is in the numerator, so of all of this, the maximum is 0.01. Cosine, the best way to do it is to just realize that the maximum value of the cosine of any angle is 1. So you just replace that by 1. And then you simply calculate that on your calculator, and that will become this number here. So that's a very tiny error. That means that even though we only use the first 4 terms, we're very close. And of course, if you didn't have a calculator, they would simply leave it like this in the section without calculator. Now keep in mind that they might rewrite it. Remember how they used to do that? It's the actual value minus this error, and it's between the actual value minus the area and the actual value plus the error. Number 48, let's have a look at that. Oh, hang on, I got to make sure it's the right page. Page 659. Is this page 659? No, it is not. Let me find that. Give me a second. Okay, so here's page, whatever it was, 659. This is going to kind of jump all over the chapter. They introduce Lagrange way early in the chapter, but I will leave it to the end. So here's number 48. It says use Taylor's theorem, don't worry about that, to obtain an upper bound for the error, which is the maximum error of the approximation. Then calculate the exact value of the error. So we have arctan of 0.4, they're saying is 0.4 minus 0.4 cubed over 3. Okay? So obviously our ugly number is our decimal 0.4. It's close to 0. So if I replace the x by 0.4, this x cubed over 3 becomes 0.4 cubed over 3. So the approximation I get is 0.37866. Now, if I find the arctan, so if I do it with the table, because I'm going to need the table, and this is really unfortunate, what happens is the arctan of 0 is 0. Now, the derivative of arctan is 1 over 1 plus x squared. Replace x by 0, you get 1. The derivative of this is this. When you plug in x equals 0, you'll actually get 0. And then here's the third derivative, the fourth derivative, and of course it was n equals 4. I don't know why. The book said n equals 3, but I'm doing n equals 4. I don't know why. But anyways, okay, so, and here would be the fifth derivative. So you need to go one beyond. Now, the interesting part about this is every other term is 0. So even though they stopped at x cubed, because every other term is 0, you have to assume that they could have gone to the fourth. And that's why, I'm sorry, I do know why I wrote 4. Because it doesn't, you don't know whether this actually stopped at x cubed. Maybe they had gone to x to the fourth, but because that was 0, it didn't appear. So I'm going to go with x to the n equals 4, which means the absolute value of the error would be less than or equal to the fifth derivative at z times x to the fifth over 5 factorial. Fifth derivative at z is this expression right here, just replacing the x's by z's, times 4 factorial. Where am I getting this? 1 plus c squared over 1. Oh, I'm just simplifying that. Okay, so, no, I'm not simplifying that. Let me stop. Okay, sorry, I don't know where I had that z squared plus 1 to the 1. I don't know where that came from. Anyways, so here's our fifth derivative at x. So here's our fifth derivative at z. Here's our 5 factorial. Our x is 0.5 to the fifth, where z is between 0 and 0.4. 0 being our pretty a, the 0 that our ugly 0.4 is close to. Okay, so simplifying this, it becomes this expression right here. So this is where the variables are, and in order for that, which actually is 5z to the fourth, blah, 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 over z to the 10th, right? Z squared plus 1 to the fifth, the highest degree will be z to the 10th. So in order for that to be a maximum value, the denominator's got to be a minimum, and that's going to happen when your z is 0. So what you're going to do is replace, sorry, that should be to the fifth. Okay, so that's to the fifth. So we're going to replace all these z's by zeros and simplify that expression, and that'll give us 0.002048, and that's the maximum possible error. Okay, the Lagrange worksheet. Let me pull that up. Okay, so here's the Lagrange worksheet, and we are looking at number 2. So let me make that a bit bigger. So in exercises 1 through 10, we've done all this before, but the key thing is it says find the Maclaurin polynomial stated degree for the function f with the Lagrange form of the remainder. So that's what we're going to concentrate on. So we're looking for a Maclaurin series, which is near 0 for f of x equals 1 over x plus 3 of degree 5. Okay? So we make a table, and I'm not going to go through the whole thing, but you would find all the derivatives. Because it's degree 5, you are going to have to find the sixth derivative. And for now, just use your calculators and find the sixth derivative of 1 plus x over 3, which will give 720 over x plus 3 to the 7th, because I'm just interested in the Lagrange form of the remainder. So the maximum error I'll get when I use the first 5 terms will be less than the 6th derivative at z over 6 factorial times x to the 6th. So my 6th derivative at x is 720 over x plus 3 to the 7th, so I'll replace the x by z. Z is between 0, which is my a, and x, but I don't know what x is here, so I just have to leave it as between 0 and x. So this will simplify down to 720, just make a single fraction out of it, like not a complex fraction. 6 factorial is 720, and so you'll be left with that expression. And that's as far as you can go because you don't know what x is. So you can't replace x by anything or z by anything because you don't know what x is. Okay. Number 12 from the same worksheet. So number 12 is a Taylor polynomial. Find the Taylor polynomial with the Lagrange form of the remainder. So we're looking at number 12, f of x equals root x. It's near 4, and it's degree 4. So on the TI, just find the 5th derivative, so we're ready to go. So the maximum error, if we use the first 4 terms, will be the 5th derivative at z over 5 factorial x minus 4 to the 5th, because it's a Taylor here. And therefore, the 5th derivative at z, I'll take this expression, replace x by z, turn it into a single fraction. Z is between a and x, which in this case is 4 and x, but I don't know what x is. And so therefore, that's as far as I can go.